Okay, I think from there you can then join. Yes. So good evening everyone. So this is our 11th problem solving session for the course Nanomaterials and Properties. Mhm. So there will be one more session after this. I'm not taking the revision session this year. So brief recap of the content covered in the lecture this week. So there are three types of magnetic material. First we have your ferromagnetic, this is your ferromagnetic, where the susceptibility is very high. Susceptibility is susceptibility. So both ferromagnetic and paramagnetic materials, ferro, they both have unpaired electrons. So which is due to spin of the due to unpaired electron and the orbitals. Okay. In ferroelectric, what happens is you have your magnetic domains, which are mostly aligned for aligned magnetic field this way. Most of them are aligned, and even if you remove this magnetic field, still a lot of them are still aligned along a certain direction. This is your H. This is your B. H is applied magnetic field strength. B is the induced magnetic field strength. In case of paramagnetic materials, yes, they also have unpaired electrons, but uh, the magnetic domains do not interact very strongly, and uh, they are randomly oriented. Once you apply magnetic field, some of them will orient more or less in the direction of the magnetic field, and on others you can see they align to the direction of the magnetic field. So this is strongly attracted. This is weakly attracted. To the magnetic field applied. And finally, we have diamagnetic. Here, uh, the electrons are paired. So they do not have magnetic moment due to the electron in the orbital. What happens is when you apply magnetic field, they have they align themselves opposing to the applied field. So H, there will be small magnetic field induced in the reverse direction. The susceptibility is very small, so compared to this one, is like 10 to the power 6, 7, 11 autos, so it is very easily repelled. And the magnetism is due to just the spin of individual electrons, not the orbital motion around. Yeah. We have paramagnetic metals, that are soft and hard uh, magnets. So in paramagnetic material, initially when magnetic field is zero, they are all randomly oriented. However, when you apply magnetic field, there is a magnetic field induced inside the material. So as you increasing the magnetic field, some of them start to orient themselves along this applied magnetic field. As you increase it, more and more of them starts to align with the magnetic field. And after reaching uh, a maximum where all the domains are now pointing in the direction of the magnetic field, so all the domains are aligned with the magnetic moment, you reach a saturation point that no more magnetic, there is all the domains are in this direction, so no more rotate. Okay. So in this curve, it was it was the case if you're starting from zero. However, now that you have introduced magnetic moment inside the material, now even when you remove this applied magnetic field, there will still be some magnetic uh, induced magnetic field left. The material has been magnetized. You apply paramagnetic, you apply some magnetic field, apply some magnetic field, it saturates. Now you remove the magnetic field, it doesn't go down to zero. This again it saturates in the opposite direction. Mm, started from zero, you start applying magnetic field. Uh, Domains are aligning slowly. At this point, all the domains are pointing along the direction of applied magnetic field. And you start reducing the magnetic field. After some time, you've removed all the external magnetic field. Still, there is internal magnetic field, induced magnetic field left. So you're now polarized your magnetized your material. It becomes a permanent magnet now. Okay. But to remove this magnetic field, now you need to apply opposing magnetic field. So this material, if the magnetic field was generated in this way, you need to apply magnetic field P is in this direction, as you need to apply the opposite direction. So now you're increasing the magnetic strength, and after reaching this point, now you've removed all the induced magnetic field. So it's zero now. So there are few points. This is your saturation magnetization. Saturation magnetization, the maximum magnetization will give. This point is your coercivity, where the in where you apply the opposite magnetic field and the total magnetic field becomes zero. So induced magnetic field becomes zero. Now, if you go even further in the reverse direction, we'll hit the. So now magnetic fields are starting to orient themselves to this direction. This is the direction X. The domains are starting to orient themselves again to this magnetic field. And after reaching this point, again all the domains now point in the direction of the magnetic field edge. Again, we increase the saturation. We increase the magnetic field further, nothing will happen. The saturates. Again, if uh, you remove the magnetic field, now the your material is magnetized in the other direction. So this point is called remnants, the remaining magnetic field. Okay. What are soft and hard magnets? So it's just about the area of the square. Soft magnets have a smaller area. This one has lower area, so this is soft magnet. And this has larger more area, so hard magnet. How much will be usable to live larger area? Next, we talk about the magnetic domains. Then you have your individual grain. This is your grain material. And you have your atom sitting in your crystal structure, right? So this CC in the face, CC. So each of these substance, you have unpaired electron. Something like this. We have unpaired electrons. So each of these atoms have small magnetic field. And one zone, all these magnetic fields will point in single direction in a particular area. That area you're calling is a single domain. In this domain, all individual magnets, small tiny magnets formed by atoms, are pointing in the single direction. Okay. Then in the same grain itself, there will be kind of a magnetic grain boundary inside the grain. Okay. This block wall, we are not calling it grain boundary, we are calling it a wall. So between the grain domains, we have your magnetic domain walls, and across this wall now, the domain is pointing in some other direction. So what happens when you apply magnetic field? These domains start to switch and start orienting in particular directions. And the transition between this domains in this domain wall region, this is not uh, abrupt. The magnetic field changes gradually. So if in this domain it's pointing in this direction, uh, and the other domain is pointing in the opposite direction, there is like incremental change in the direction. In this case, it's out of the plane. So if you assume this was direction and this way, you have your wall and direction this way. So while switching, these vectors are pointing out of the plane, like arrow and arrow representation, point and arrow, cross and arrow. This means pointing going inside, and this is pointing outside. And this is pointing inside, and this is pointing outside. So there will go something. They will be inside this plane, being inside. At one point, it will be completely perpendicular to the surface, so completely x pointing in there, and gradually it will spin. Difficult to demonstrate in 3D, but yeah, we can imagine this. Uh, these one are pointing outside surface along this surface. The other ways they can also transition can happen inside the plane of the grain itself, along like plane of these domain walls. So it will gradually become something like this, 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 and the transition is happening inside the plane. So the lengths are equation. So this is when it's out of the plane, this is called block wall, and this is wheel wall. Where's the question? It's wall. Next you have ferromagnetic, super ferromagnetic and super paramagnetic materials. So now you're reducing your grain size. Now your grain size is so that this becomes if your grain size. Okay. That the grain size becomes comparable to the domain, magnetic domain size. So if the grain size is larger than 100 nanometers, somewhere around that, you're in multi-domain region. So each grain has multiple domains. So this way, uh, this way. This is a multi-domain region. Where if you start reducing the particle size around 10 nanometer and 30 nanometer, you start entering the single domain region where uh, this example. Now your each single grain is pointing in a specific direction. This is a single grain. All the domains are pointing in the upward direction. Okay. So what's difficult is changing the orientation of these domains inside the grains between this in the transition zone in the block wall region. It takes energy to move all these domains to align them in a particular same direction. However, when you once you have your grain size itself very small and there's a single domain inside individual grain, now they are much more easily uh, easier to move around and can easily align themselves with each other. And then you get your super ferromagnetic material. Yes. Yeah. It's very easy to magnetize these materials and this remain magnetized. Yeah. However, if you go down further, if your grain size is now 1 nanometer or smaller, you enter the region of super paramagnetism. Okay. In single domain, you have two zones, your super ferro, and your super para. In super paramagnetism zone, what is happening is now your grain is very small. So now what's happening is your thermal energy, KT, due to the thermal vibration itself, that energy is more than the magnetic energy between the interaction energy between the particles. Now the thermal motion can break this magnetic interaction between them, and uh, now this domains or grains are pointing Since each domain, one brain has one domain, you can use them interchangeably. So each of these domain now point in random direction due to thermal motion. And since they're randomly oriented, they cancel out the overall magnetic field. Or when you apply some magnetic field, they'll still align themselves somewhat, uh, giving you a small attraction. Next was what can happen to light if you shine some light on a interface. So you have a glass and air. So once when the light reaches here, some part of it will get reflected, some part will get absorbed in the glass, and some part will get transmitted. Okay. So some fraction is reflected, some fraction is absorbed, and some fraction is transmitted. However, the total of these three terms, reflection, absorption, and transmission, has to be one, which will be equal to the total initial incidence energy. So I that is equals to I reflected plus I absorbed plus I transmitted. Okay. So your if you take absorbed, your I can be represented in exponential form. I is equals to y naught is equal to x. And if there are two boundaries, enters this returns parallel this way. So we have reflectivity n1, n2, and 3 enters, some part is absorbed or reflected. Okay, reflection. Some part is reflected over here. This is accounting for both these reflections, so multiplying it twice. So intensity after reflection. And yes, Snell's law gives you the angle between this is a theta 1 and the theta 2. Next, we have excitons. So excitons are the reason we get superconductivity in materials. So what's happening is from valence band, one electron jumps to the conduction band. Right? Now you have a positive pole left here, an electron over here. Now if they remain close to each other, what will happen? There will be a Coulombic attraction between these two. That will kind of reduce the energy required to uh, excite this electron. So if this was the energy gap, there was no uh, interaction between this P plus and whole H plus and electron. If there was no interaction, this is the energy you will need to give equal to the band gap to separate them. However, if there are there is a Coulombic attraction between these two, they're close by, that some of that energy is compensated. So it's like this much energy that is being compensated by the Coulombic attraction. The band gap Eg will be equal to the Coulombic attraction plus this excited energy difference between this excited levels. And yeah, even when this electron hole pair is moving, they remain kind of bound to each other, forming kind of a hydrogen atom. The H plus and the E minus will spin around depending on the effective mass. They can be similar actually. In in case of hydrogen atom, your proton mass of proton is much larger than mass of electron. You they kind of spin. Proton is at the center, electron spins around it. Right? But however, in case of semiconductors and materials, this hole and uh, electron can have similar electron mass. Um, be similar. So now, since they're similar mass, they'll spin around each other like a two body system. Next, how does the size affect the optical absorption spectrum? Here you have absorption spectrum of particles with different size. Okay. Do you remember this equation for a single particle in a box? So there you go. Energy is proportional, inversely proportional to dimension L square. If L decreases, the delta E increases. What happens now? Since delta E, the band gap is increasing, you need to give higher energy. So energy of your incident photon Hg is higher. Since its energy is higher, its wavelength is lower. Okay. So what's happening is the absorption peak is shifting to lower wavelengths as you're decreasing the particle size. L is decreasing, the wavelength, absorption wavelength, this peak is shifting this way towards the lower wavelengths. And this would be called your blue shift. If it's moving this way, blue shift. And if it was moving that way, this is mentioned. 52 red or blue side. Red has higher frequency, so this way is red, this way blue. Uh, okay. So in this case, this will have larger particle size, will be red, will be more than the blue. Finally, we have plasmons. Plasmons is surface plasmon, coherent oscillations of electron that occur at the interface between metal and the dielectric like air or water when light hits the metal surface. So we have a light wave passing light. So light is formed of electromagnetic oscillating electric and magnetic field. So due to this oscillating electric field, it will induce a oscillation inside this uh, free electrons in the metal. They'll also oscillate with the oscillating electric field. So this collective oscillation is we call it as plasma. As the particle size changes, actually the particle size becomes comparable to the wavelength. This plasma effect is more visible. Some practice questions. Which of the following parameter is used to assess the magnetic ability of the material? Uh, Susceptibility, right? Yeah, psi, depending on its value, but less than zero. Yeah, the magnetic goes to zero, but positive, it's paramagnetic, and it's very large here, yeah, paramagnetic. Depending on the susceptibility, we classify the material. Magnetic ability of material. For a diamagnetic material, so diamagnetic means yeah, uh, all the electrons are paired. Which of the following statement is correct? Related permeability. So mu is equals to mu naught 1 plus m. Relative permeability is mu r is equals to mu over mu naught, which is equals to 1 plus xm. For diamagnetic material, xm is smaller than 0. This is right in 1 minus some number x will be slightly smaller than 1. So lesser than 1. So relative to the 0 is 1. Yeah. What is Here actually. For paramagnetic material, which are the following grade? For paramagnetic material, which of the following statement is correct? Here this magnetic susceptibility for paramagnetic material is greater than 0. It 0 is for vacuum, less is for dia, this one nothing. The temperature of antiferromagnetic to ferro to paramagnetic transition, I think we already did it last class. Just definition. So this is the Neal temperature where your antiferromagnetic material, yeah, alternating magnetic domains becomes randomly oriented. That's your Neal temperature. As we decrease the dimensionality of particle, the magnetic moment. In general, initially the magnetic moment is increasing. As we decrease the dimensionality, magnetic moment increases. In multi-wall domain, okay, so in multi-wall, this known coercivity increases with coercivity is increasing with decreasing the particle size. So, going to smaller particle size, decreasing the particle size, coercivity will increase. In single domain, it initially remains unchanged, saturates, then it drops off, reduces sharply. In single domain, coercivity, it decreases. So it's decreasing as you're going this way. Yeah, decreases with this particle diameter. The thermal equilibrium concentration of electron in the conduction band in the hole in valence band depends on. So for formula is N naught, which is your electron concentration, is equals to the density states and collection band and temperature T half EF minus E conduction KBT and density clearance concentration of holes is V T R EV minus K. Okay, so the equilibrium concentration, it depends on the density of states. This is the effective density of state. And also depends on the Fermi level, where the Fermi level is. Technically also depends on the energy level of the valence and the conduction band, but in class. Only both A and B are correct, so C is the correct option. What is exciton? Exciton we just saw is a bound state of electron and a hole pair. Here that electron, the hole, positive, they're bound to each other by Coulombic attraction. And because yeah, with reducing the size of the particle, which properties of the semiconductor changes? Both as you're reducing the particle size, your band structure is becoming discretized, right? And create. So density of states has become quantized. This is your number of states, density of states. Band gap also shifts to higher energy. So as you're reducing the particle size, as you're increasing R, sorry, decreasing R, is decreasing in this direction. Your band gap increases. Band gap shifts to higher energy. So, more questions. Diamagnetic material, these are now relevant to next week of assignment. Yeah. So diamagnetism in material arises due to, like, diamagnetic material. They have their holes are holes. Their orbitals are completely filled. Not completely filled, but all the electrons are paired up to each other. There's one up pushing, up spin, down spin, up spin, down spin, up spin, up down, up down. All of them are paired. There is no unpaired electron. This is correct. And might affect electron spin and angular momentum? No, since there's no angular orbital momentum, since they don't have an unpaired electron, so this is not there. This is only due to the orbital motion of electron. What kind of magnetic material is the copper? The if you know the electronic configuration of copper, is argon 4s1 3d10. 3d10 means your d orbital, lowest orbital is completely filled. Since you have all your 10 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Since your d orbital is completely filled, this diamagnetic area of the BH loop. So, BH loop. What does this area inside this BH loop tell us? That is the magnetic loss. Magnetic energy magnetization is how much magnetic field is induced. It's the loss of magnetic energy. So if you remember the transformer example, you want this area to be as small as possible. You still want to go to the same level of magnetic field, but you want area to be smaller as compared to like this. So you want a softer magnet. So for transformers, you want soft magnets. You lead to lesser loss of magnetic energy, more efficient transformers. State whether the following statement is true or false. Domain and grain are of same dimension. This is not true because this if this is your grain size, you can have multiple domains where the magnetic field, the induced magnetic domain are pointing in another direction, different directions. This is false. D of domain is less than, can be equal, but that's only in case of uh, very small grains. Most of the time, it will be less than size of grain. Remember that. Dash have spins rotating in the plane of the wall. This was your domain 1, so domain 2. So to get from domain 1 to 2, you have your wall. So when this wall rotates in the plane of this, magnetic spins are rotating in the plane of this wall, and you call Neil ball. So you started from this direction, slowly moves You had one ball pointing this way, when one domain spin is in this direction, the other is this direction. It is slowly transitioning. Here we go. State whether the following statement is true or false. In superparamagnetic region, coercivity has a strong dependence on grain size. The superparamagnetism mostly comes to play in this zone. Here, thermal energy larger than your kinetic energy. In that case, coercivity is almost zero and is independent of the grain size. It's false. Harmonic magnetization. So, from this plot itself, as you can see, for superpyramidal materials, coercivity at luminance is almost zero. Zero. State whether the following statement is true or false. Excited formation allows the electron to move from valence to electron even if excitation energy is little smaller than the mass. This is true. Yes. This is the energy you require to, if you didn't have a site on levels, this is the energy you will require. H2. So H nu has to be greater than equals to the band gap EB. However, when you have your exciton level is smaller, so now with energy less than this H nu, EB, still your electron can move from valence to conduction band. True. So what happens to the absorption energy of the spectrum as the particle size increases? So your particle size is increasing. Yeah. Particle in the box. Energy is inversely proportional to L. As you're increasing the particle size, L is increasing. The energy level En is decreasing. So delta En is also decreasing. Okay. If the band gap is decreasing, you need the energy H nu is lesser. That means your wavelength is larger. So as wavelength is larger, that means you're shifting to right side. In this way, so red shift. What leads to blue shift of the absorption spectrum with decreasing nanoparticle size? This is happening due to quantum confinement, right? As you're decreasing the particle size, their energy levels are moving further apart. So due to mainly due to quantum. Next, we can discuss assignment. Okay. Below a critical value of grain size, the nanomaterial transforms to. So as your grain size becomes smaller and smaller, it more or less starts behaving like amorphous material. What's amorphous material? There are no grain boundaries. There is no boundaries or other terms are oriented randomly. Since you have very small grains, the number of grain boundaries will increase a lot. Increases, right? All these grain boundary regions are where you have randomly positioned atoms which do not follow some specific lattice. We are moving more and more toward amorphous material. A large number of rings. Okay. State true or false. Statement is stress concentration in a given grain increases as the grain size reduces more and more. Up to a point, the stress concentration does increase, but until smaller, you can have filing, spec dislocation filing will start sooner. However, if your particle size is very small, there's no filing, but there's the stress concentration doesn't increase further. This is true for until a certain point only, so not generally. So that's why it's called inverse on patching. So after a certain point, you start to see breakdown of the Hall patch equation, and then your inverse Hall patch vector strength actually decreases. Liquid has the liquid doesn't have any crystal arrangement, so it's actually the marks. Yes, and solid melts to liquid crystalline mass. Solid liquid transformation at melting temperature. So if you remember the fluid diagrams, that statement is a liquid, liquid is. So at the solid liquid transformation, at this point, there will be equilibrium between the liquid and solid phase. At that point, your delta G of liquid will be equal to delta G for solid and delta G for solid. Because you're at the melting point, exactly at the melting point, it's an equilibrium. Both states have equal equilibrium. How does the shape of nanoparticle influence the melting temperature? Yeah, shape can affect. Shape will affect the surface to volume ratio, so thereby will impact the melting temperature. Specific geometry of the nanoparticle affects the surface to volume ratio. Different shapes, the sphere, wire, and film will have different ratios, which in turn causes their melting point to vary. Thermal conduction in insulators take place due to, do you remember, in the case of diamond, thermal conductivity is somewhat kappa lattice plus kappa electronic. Since it's an insulator, kappa electronic is 0, so you only have kappa lattice. Kappa lattice is due to the phonon vibration of the phonons. How do increasing atomic vibration affect the resistivity of the cell? So your resistivity or your inverse is conductivity, sigma. So 1 by rho sigma. It depends on two things. First is your relaxation time, tau. Second is your density of states, and density of charge carriers. So number of electrons, and your relaxation time. Relaxation time is your electron is moving. How long does it take for one consecutive collision? Tau. Collision between the lattice. So we are increasing the atomic vibration. So these atoms are increasing, vibrating more vigorously. Their effective size will increase. So your tau will decrease. Tau will decrease, sigma will decrease, and your resistivity will increase because there will be more frequency scattering. What is the main factor determining the band structure of a semiconductor? Resistance structure, the quantum, you know, band structure for 3D looks something like this. Confine it in one direction, it becomes staircase like Z. If you confine it in two directions, it becomes like this. Right? And you confine it in all three directions. Usually discrete. As a waveguide, nanomaterials are used because electron are confined length. So waveguide usually they're 1D material. In 1D, your confinement is in two dimensions. The rods are confining it in two directions, and electrons are moving along the direction of the tube. It's already mentioned in the tube, along the axis of the tube. Also in the 2D length of the tube. Which of the following is direct consequence of quantum confinement? We just saw, right? Discrete and separate energy levels. As a quantum confinement, energy becomes inversely proportional to L square. So your energy gap actually increases. And so from here to here, your particle size is decreasing. Energy gap increases or decreases. continuous ancillars and become discrete separate energy. Quantum confinement is observed in the particle size. So this is happens below 5 nanometers. Lot. Yeah. It generally happens below 5 nanometers. Okay. So that was all. Uh, Next assignment is due on 8th October Wednesday. Be sure to complete it. If you have any doubt, you can ask me now in the chat. Any other assignment or practice questions. Okay, no questions. You can end it here. Thank you for attending.